Hi, welcome everyone to the session 9 of Mentoring for a Career in Machine Learning course. So, in this course, we will talk about regression using KNN. So, KNN stands for K nearest neighbor. So, in this session today, we will understand what is this concept of a neighbor and how do we take help of the neighbors, right, to predict the value or the behavior of a new entity, how these neighbors are computed, and how the prediction of the new entity is estimated. It's a very popular algorithm, KNN, and widely used in scenarios where uh, the the entities which are very similar in attribute, they show very similar behavior or has a similar value. So for this session, I have uploaded notebooks to a new directory that I have created called session 9. So there is a new notebook called regression using KNN v1.ipynb. So let's go to that particular notebook and open that in the Jupyter notebook. And again, we'll be using uh, the the car's resale value data set and what we have been experimenting so far, and we have already built a model using linear regression, and we will be using that and build a KNN model and compare the accuracy of the model with the previous models. So let's go ahead and load the data set. So this notebook, the code is already given. So we'll just run through and understand different concepts and execute step by step. And at the end of the notebook, I have given a few participant exercise. So after the session, you can actually work on those exercises and upload to the your respective GitHub folders. So let's load the data set, import all the required libraries, the pandas, numpy, matplotlib, and shebun, and load the data set, which is final cars maruti.csv, and look at a few samples. And we have already gone through this. So you know there are about 1010 entries are there and about 11 columns, and out of that one is the outcome or target variable, the y, and the remaining all are features. Powering off. So the whole idea here is, let's say you want to predict the price of a new used car. Let's say the car is, of course, it's a Maruti car because we are building a model only for a Maruti car. And let's say the model is a Swift, and it's a petrol car, and it's an automatic. It is driven for, let's say, 40,000 kilometers and about, let's say, 5 years old. So to predict the price of this particular car, right, how can we take help of the examples that's there in the training data set? So rather than looking at all the examples in the training set, what we can do is we can only look at those examples or those instances which are very similar to this particular car. So maybe we look at only the cars which are Swift models and petrol and automatic. So let's say we have some samples which are similar, the same model, the same fuel type, and the same transmission type. But maybe we don't have examples which are driven exactly 40,000 kilometers. So maybe there are cars which are 39,000 kilometers or 42,000 kilometers. So which are very near to this particular car. And let's say we don't have any car with 5-year-old, let's say 4-year-old. or 6 years old. So we look for those instances or examples in the training set which look very similar to this. And then we'll take help of those examples and their prices at which they were actually sold, and from that we'll estimate the price of this particular car. So these examples are called what? They are called neighbors of this particular sample. So how many neighbors we will look at? That stands for K. So K stands for, it's a variable, we call it a hyperparameter. We'll look at that. And the nearest neighbors. And from there, we will estimate the price of this target example. So now let's understand a little more in detail what are the key ideas and how do we actually compute a neighbor, right? And how do we actually predict? What are different methodologies are there? What are the different pre-processing steps or constraints we have that we must follow before building the model? The first we'll look at what is a neighbor. We've already understood a little bit, but we'll go a little deep dive into it. But for this, we will only consider two attributes called age and kilometer driven. Because we can't visualize anything more than two variables, so we'll just stick to two variables as of now and understand the concept. So we'll create a small subset of samples from our original sample. We'll take only 10 samples and we will take only age, kilometer driven and price, these three variables, and we'll look at that. So these are the, let's say this is the training set we have right now. This is the training set we have right now, in which we know there are 10 examples are there, and we know how old those cars are, from 2-year-old to 10-year-old, kilometer driven, which is like 4,000 kilometer to 1,30,000 kilometer, and their respective prices at which those cars are sold. Now let's say we'll depict that in a scatter plot. So the x-axis is age and y is kilometer driven. So now if you look at, if I ask which is the neighbor of this particular example, right? So this car is probably about 5-year-old and it has been driven about 60,000 kilometers. So 5-year-old and has been driven about 60,000 kilometers. So now, what are the neighbors of this particular car? We can visually see that, of course, this is one of the neighbor and this is the other neighbor and so on and so forth. But mathematically, how do you do it? So because this particular car is also about 5-year-old and driven probably about 70 or 72,000 kilometers, and this is about 6-year-old and driven probably around 50 or 55,000 kilometers. So compared to other instances that we have in the example, so these are the nearer ones. Right? So cars with very similar attribute, in this case a similar age and kilometer driven, are called neighbors. So for this particular example, probably this will become called neighbor, the first neighbor and the second neighbor. And similar cars will have a shorter distance. The similar car will have a shorter distance, that they will be nearer to each other on this Euclidean space. This is the Euclidean space, right? Up to dimensions, age and kilometer driven, compared to dissimilar cars. So if you compare now this car, let's say this is N3. So of course, N1 is nearer compared to N3. And this can be, of course, depicted using the concept of distance or Euclidean distance. Then how do you calculate the Euclidean distance? The distance between, of course, if you depict the car as x and depict this car as y, the difference and the distance between these two cars would be the age of x minus the age of y square plus the kilometer driven by the car x and the kilometer driven by the car y square, and take a square root of it. This is of course from the perspective of two variables or two attributes, but this can of course be extended to n number of variables or attributes. So what is the distance between two cars? So let's find out which cars from the sample. Let's say there's a sample of 4-year-old car and has been driven for 30,000 kilometers. So let's compute that. So for this I have defined a particular method called car dist, which takes the age and kilometer driven of the car X and age and kilometer driven of the car Y. And we'll take this value and we'll square age X minus age Y and a kilometer driven minus kilometer X minus Y square and take a square root of it. And then of course I'm rounding it up to 2 decimal values. So now if I send information about two cars, the car which is driven for 50,000 kilometers and of 10-year-old and another car which is 4-year-old and has been driven for 30,000 kilometers. So what the distance would be? It's about 20.88, right? So similarly, I can calculate the distance between the cars. So let's say I am given the distance, I've given this particular car's information. So I can calculate the distance between all the cars, because mathematically if I were to compute on a very large data set and number of variables, of course we can't visualize that. So we'll calculate the distance with respect to remaining all, let's say, examples, and then we'll sort them by the distance. We'll sort them by distance. So the examples which are lesser distant, the minimum distance would be the nearer cars. So we'll go ahead and now apply this particular distance method now. So car subset df apply to each of the records. So we'll call the car distance and we'll provide age and kilometer driven of that particular record. So if you want to find out what's the distance of all these cars from a car which is 4-year-old and has been driven 30,000 kilometers, so we'll go through each one of them one by one and calculate the distance. So apply is a method which can be applied row wise for a data frame. So take a data frame dot apply, and what it gets is a record. So you'll get each record of the car's subset D of the data frame, and then we'll take the age and kilometer driven parameter and pass it to car distance, and in comparison to the car that we want to measure the distance from, which is 4-year-old and has been driven 30,000 kilometers. And axis equal to 1, that means we can apply the method row wise or column wise of data frames. So if you take a data frame, right, we have columns and rows. So if you want to apply a particular method, iterate through that. So if you want to row wise, you can say axis equal to 1. If you want to column wise, you can say axis equal to 0. And then once I calculate the distance of all the samples in this particular subset from the car which has been driven for 30,000 kilometers and 4-year-old, then I will sort them by the distance. So if you look at this, this distance is 0 because we already have a car which is 4-year-old and 30,000 kilometers. So definitely the distance would be 0 to that, right? and this is 3.16. So the next or the nearest car, which is 5-year old and has been driven 27,000 kilometers, and so on and so forth. But is this distance calculation correct? So let's look at another example to kind of intuitively find if the distance calculation is a little distorted, and do we need to do some kind of pre-processing before we do the distance calculation. So let's look at another example where we want to find the distance between the customers. We want to find out which customers have a similar behavior or demographics compared to the other customers. So let's take, so this is a data frame created with information about only 4 customers to kind of understand this concept. Let's say the customers are called A, B, C, D, and their age, which is 20-year-old, 21, and so forth, and income is probably ranging from 10,000 to probably 90,000, right? So let's look at the customers. So these are the customers and their information. Now, if I have to find which customer is very similar to A, customer A, so in terms of age and income. So if you look at here, probably the customer B is very similar because the age is just 1 year difference and income is not much of a difference, it's just a difference of 1,000 rupees. Whereas if you look at A and C, the customers have a difference of age 50-year-old, so they're very different in terms of age, and income again not much different, but from the perspective of income not much different, but the age is very different. So I would say A, B are very similar in demographics compared to A and C. So when we calculate distance in Euclidean space, does it also say the same thing, that A and B are similar compared to A and C? So let's look at customer distance. So again, like car distance, I will send the age income and age income of 2 customers, and I'll square and take a square root of that. And if I calculate the distance between the customer A and customer B, which is 20-year-old and income of 10,000, and the other customer is 21-year-old and an income of 11,000 rupees. So if I calculate the distance, it says the distance between customer A and B is about 1,000, but customer A and C, which is 20-year-old and this customer is 70-year-old, and the difference of income is about 500 rupees. So if I do the distance calculation, it says that the distance between A and C is about 502 compared to A and B, which is 1,000. So the distance basically says that customer A and C are very similar compared to A and B. But intuitively, if you can see that from the data, A and B are similar compared to A and C, right? So there is, of course, the distortion made by the distance calculation here, primarily because the age is depicted mostly in the range of 0 to 100, right? But income, if you see, is depicted from like 10,000 to 90,000, right? So the difference in age, even if it's a 50-year-old, so it only amounts to 70 minus 20, it's just a 50 square. But income, if you see, the difference in income of 11,000 to 10,000, right, which becomes 1,000 square. So the Euclidean distance that we calculate between entities here are typically determined mostly by the income, not the age, because age is typically represented in a smaller scale compared to income. So a small difference in income of 100 rupees or 200 rupees will have a very greater influence in the distance compared to the age, even if there are 50 years difference or 40 years or 80 years difference. So this is one of the problems in distance calculation, which has to be resolved by using a technique called scaling. That means even before calculating the distance, all features had to be brought to one single scale. Right? Only then the distance calculation would make sense. Otherwise, the distance would always be determined or overwhelmed by the features which are represented on a higher scale, a larger scale. So the conclusion here is distance wise A and B are very different, whereas A and C are similar. But in reality, A, B are similar compared to A and C. That's what we have discussed so far. This is because of difference in scale in which age and income are represented or measured. So for any algorithm, not only KNN, any algorithm which takes help of distance calculation. Right? So the first thing you have to do is you have to pre-process the data to bring all the features into one single scale. So then what are different scaling techniques are there? One is called mean max scaler and the other one is called standard scaler. There are two important techniques that are used for scaling the features. Min max scaler is it looks at the feature. For example, if you look at this only four different observations, so it looks at age. So how do we scale it? Now look at what's the minimum value of age in across all the examples. The minimum value is 20. The maximum is what? 70. So this should be the starting point and this should be the end point. So this is actually converted into a scale of 0 to 1. So 70 minus 20, that's a difference. Now, any of these observations are how far away from the minimum on this particular scale. For example, let's say you are again 20-year-old, so 20 minus 20. So you take any observation xi minus x minimum divide by x max minus x minimum. So if you look at this will be 0 because you are at the start of the scale itself. And if you are 21, then it will be 21 minus 20 divided by 70 minus 20. So it will be 1 divided by 50. And if you are 50-year-old, right, it will be 50 minus 20 divided by 70 minus 20. So that will be 30 divided by 50. Right? And of course, if you are 70, it will be 70 minus 20, that will be equal to 1. So how far away you are from the minimum point, okay, on the scale of maximum minus the minimum. So this particular scaling technique will convert all the features into a scale of 0 to 1. So in this technique, the minimum value of the feature is scaled to 0 and the maximum value is scaled to 1, and all other values are scaled to a value between 0 and 1 based on the relative position to the minimum and maximum values. So we convert this data into x norm equal to xi minus x minimum divided by x max minus x minimum. Similarly, if you look at the income, the maximum value is 90,000 and 10,000. So if your income is 11,000, so how far away on the scale? That will be 11,000 minus 10,000 divided by 90,000 minus 10,000. So this will be like 1,000 upon 80,000. So now you can see the scale will have a appropriate influence on the distance calculation. The other technique to convert or to scale features is called standard scaler. This of course assumes that the variable follows a normal distribution. So if you remember, we discussed about normal distribution. The whole population lies between -3 standard deviation with a +3 standard deviation, right? So what we do is uh, we find out a particular value is how far away from the mean value or the average or x bar or mu in terms of standard deviations. So it is 1 standard deviation to the left or 0.5 standard deviation to the right or 0.5 standard deviation to the left or right, and so on and so forth. And of course, the value is calculated as the xi minus mu. Mu is of course a sample mean, a population mean. We may not have access to the population mean, so we'll calculate the sample mean divided by the standard deviation of x. So data processing technique used in machine learning to transform features of data set. So the value have a mean of 0 and standard deviation of 1. So if your value is very close to mean, so your value will be 0. If your value is very far away from the mean and lesser than the mean, so it will be like negative value in terms of standard deviation. Higher than the mean, it will be plus in terms of standard deviation. Okay. So this should scale the data mostly in the range of -3 to +3. Assuming that most of the value lie between -3 standard deviation to the +3 standard deviation. There might be some outliers. If there are some outliers, of course the value will be lesser than -3 and +3, but most of them will be again -3 to +3. So here we don't assume any distribution. We simply convert them into on a scale of 0 to 1. And here of course we'll convert into a scale of -3 to +3. But whichever technique we use, we bring all the features into one single scale. So the distance calculation becomes easier and it makes a lot of sense. So how do we do that? So in this particular example, we will only use mean max scaler. The standard scaler, we will keep it for future sessions. And there are of course many other algorithms which take the help of distance calculation. So we will explore standard scaler in one of the future sessions. So if you look at the sklearn source for mean max scaler, it also says that x minus x mean, x max minus x mean, and that's how the value is calculated. And it brings the data between 0 to 1. So you just have to import this, instantiate and apply to the data. And the other one is standard scaler here. Okay, again it basically says that the value minus the mean divided by the standard deviation. So how do you actually invoke that? So from scikit-learn pre-processing, import mean max scaler, instantiate mean max scaler, then you can call fit and transform. Typically you should first call fit, which will estimate the value of mean and max, and then transform, but you can also apply at the same time. This is just to understand the concept. We'll actually explore how to appropriately invoke that in building pipelines in the later part of the notebook. So scalar dot fit transform, so customer DF age and income. So scale data. Now the data has been scaled. So if you look at the first one, it's scaled to 0, 0, because I think in terms of age and income, both are minimum here. So 0, 0. And then the respective ones. For example, this is the maximum value of age and this is the maximum value of income. So they will be appropriately set to 1 and 1. And other values are calculated based on those. Now let's assign these two as a new columns in the cust df. So customer A, which is age is 20, age is 20 and income is 10,000. Now the normalized value based on the min max scaling is 0, 0. It's 21 and 11,000, 0.02 and 0.01250. And here is 70, which is the maximum age, represented as 1. And in this case, this is the maximum and represented as 1. Right? So all the values are appropriately represented now. So now if I go and calculate the distance between A and B, so this is A and this is B, and if I use the normalized data, and now it says the distance between customer A and B is 0.02, whereas distance between A and C is 12.0. So now if you see, it says the customer A and B are very similar compared to A and C, which makes sense because they are very different in terms of age, and there are hardly any difference in terms of income if you look at the complete range itself. So this is very important, that we scale the data and bring all the features into one single scale before we compute the distance, because the distance will give us the right neighbors from which we can predict the outcome. Now let's look at apply this to the scaling of cars data. So whatever the neighbors that we have found before this in terms of distance, so these were not calculated on the normalized or scale data. So they were calculated the actual data. And if you see here also, typically the age, which is the how old the car is, it ranges from 2 to only 10, whereas the kilometer driven can range from 4 to 130. You can see that two different scales are here. So it only makes sense that we bring them into same scale. So we'll go and apply the same thing to the cost data, mean max scalar, and we will calculate age and the distance based on age and kilometer driven, and we'll apply fit and transform, and we'll add them as two new columns called age norm and kilometer driven norm. And if you look at the data, so these are the new scaled or normalized data based on min max scaling for different cars. And to compare them with the actual age and kilometer driven price, so let's add the original columns to this cost scale DF, which is the new data from that we have created here, so that we can compare and look at it. So this is the original age and kilometer driven of the cars, and if you see, this is the minimum one, and it's represented as 0 correctly, and that's the maximum one is represented as 1, and all the other values have been normalized based on that. Same thing here as well. This is represented as 0, and this is represented as 1, and the rest all values have been scaled based on that. So now if I go and apply the cost dist, okay, with the distance from the car which has been driven which is 4 years old and has been driven 30,000 kilometers. Now how the distance would look like? Of course, we also have to provide this data with the scale information, and we know that there is already an example of that, which is 4-year-old and 30,000 kilometers. So we'll supply the same information here. All right, and we'll calculate the distance and sort it. So if you see here, now the car which is 4-year-old and has been driven 30,000 kilometers has a distance of 0 with this car, because this has exactly same attributes. And the car which is nearer to that, the next nearer is 5-year-old with a 27,000 kilometer driven, 4-year-old with a 12,000 kilometer driven, and so on and so forth. So this makes a lot of sense. If you see, most of the cars were kind of nearer cars have very similar age, right, and similar kilometer driven. Both are taken into account compared to the previous one, where if you look at the distance calculation, right, and you can see the cars which are very old cars which are also taken as a similar cars. Okay, now if I have to predict, let's say I want to predict the, of course we already got a very exactly similar example, which is 4-year old and 30,000 kilometer driven. But let's say we don't have that sample, right, in the data, and we are asked to predict the value of a car which is 4-year old and 30,000 kilometer driven. So how do we predict? We'll take the neighbors. Let's say this is a neighbor N1 and neighbor N2. We'll take two neighbors, but we can take many other neighbors. But how many neighbors and all that, will come to that concept later. For the timing, let's take example of, we'll take these two neighbors and look at the price at which they were sold, and from this we'll estimate the price of this car, right? So let's consider two neighbors now. So how do we predict from the neighbors? So one simple technique is, if this is the neighbor N1 and neighbor N2, look at their prices. Like this has been sold at 4.45 and this is sold at 6.75. So you can take a simple average of these two plus 6.75, and we'll say the expected or estimated resale value of this used car, which is 4-year old and 30,000 kilometer driven, would be this much. So using a simple average of neighbors, so price of N1, which is the first neighbor, and second neighbor, and divide by 2. And of course, if we use k number of neighbors, you can generalize this. So you can say the y value, right, of k number of neighbors, I equal to 1 to k, and then take an average 1 by k. So that will be the predicted value of y based on the k number of neighbors. So in this case, we will take, let's say, the price of k cars, and we will of course take an average because the k cars will be 1 by k, and that will be the predicted value of the price. So in this case, just take a, let's say, take the list of all the cars, price list, from the second column onwards. We assume that this is of course what we're trying to estimate, and take these two particular values and calculate the average, which is about 5.6 lakhs. And of course, you can see there is a error between the estimated price and the actual price, which is of course will be there in case whatever model you build. The other approach is, you can also predict the price based on the weighted average calculation. Why is that? Now, if you look at the neighbors N1 and N2 in this case, N1 and N2 both are not equidistant from this particular car, right? One has a distance of 0.13 and the other has a distance of what, 0.14. So the car, let's say this particular car C1, and this is a neighbor N1 and this is a neighbor N2. So you can say that rather than taking simple average, you can say the neighbor N1, because it's nearer to C, this particular car for which we want to estimate the price, is definitely nearer compared to N2. So its price will have more influence on C1 compared to the price of N2. We will take the price of both, but we will also take into account which has a higher or larger influence in estimation compared to the other neighbors. So N1 has a higher influence because of the shorter distance compared to N2, because N2 has a little larger, relatively larger distance compared to n1. So we'll convert this distance into something like weights. So the lesser the distance, higher the weight, and higher the distance, lesser the weight. How do you do that? We can take simply 1 by distance, right? So you can calculate weight based on 1 by distance. So lesser the distance, higher the weight, right? Higher the distance, lesser the weight. And then what you do is we'll calculate, let's say in this case, we will say 4.45 multiplied by 1 divided by 0.13. So that will be the weight, plus 6.75, that's the price, multiplied by 1 divided by 0.14. Okay. So that's a weight we multiply to that. And then we have to normalize by the distance. So that will be 1 divided by 0.13 and 0.14, because both the weights has to normalize to 1. So that will be the weighted average calculation of the price. So this formula is given by first we calculate the distance, weights, then price multiplied by the weight of the neighbor 1, 1, price of n2 multiplied by weight of n2, and then the weight of n1, weight of n2, right? So that will be the predicted price of the new car, for which we want to estimate the price. So let's calculate the weight first. So the weights would be 1 divided by the distance. I'm just adding a small value to it because one of the car has a distance of 0.00, so that will become infinity. So I just add to avoid that. If you calculate that, now you can see the weights, right? Of course, if you have a exactly similar car with similar information, the weight is very high, so you can directly take this value and estimate that. Otherwise, these are the different weights. You can see the weights starts reducing gradually because the distance starts increasing, the inversely proportional. And if you want to calculate the price of the car now, so we'll take the price, weights. So this is the price of first neighbor and second neighbor, and weights of first neighbor and second neighbor. So just price multiplied by weight plus price multiplied by weight for both the neighbors, divided by the weight of both the neighbors, right? So that will be the predicted price of the car. So it comes out to 5.557 lakhs. Most of the times the weighted average is preferable or most widely used in the real world compared to the simple average, because in the real world, if you take a 10 or 20 or 30 neighbors, all those neighbors won't be equidistant from this particular entity, and based on the distance, the influence is also adjusted on the estimation of the outcome variable. So now we have understood one of the basic key concepts. One is what is a neighbor, right? What is a neighbor? Second is how to calculate distance. So in this case, the Euclidean distance to find neighbor. Third one is how to ensure that the distance is not distorted, the computation of distance. It makes sense, so we have to scale the data as one of the pre-processing step for distance calculation. And then once we scale the data, then we calculate distance and find neighbors. So find k neighbors, right? You sort the neighbors by the distance and find k neighbors. But how many neighbors is something that we're going to explore in later. And then we estimate, right? We estimate the outcome variable, okay? Either using simple average or you can use weighted average, okay? So these are the key ideas of the KNN algorithm. So what we'll do is now we'll take this and apply to a larger data set of most important variables, and then see the accuracy of the model. So using more features for used car now. So let's say in this case, we will take these 6 features. Again, I'm not taking all the variables. I'm leaving that as an exercise to you to use all the variables and compute. But I'll take this 6 most important variables here. What's a fuel type? Petrol or diesel? It's automatic or transmission? The first and second or third owner? How old the car is? What's a model? And how many kilometers driven? I think the 6 most important questions that people ask, right, when they buy a car, a used car. So those will be my X features now. And out of that, of course, some of them are categorical and some of them are numerical. So I will represent separately as a 2 separate list. One is called cat vars. So fuel type, transmission, owner type, and model are categorical features, and numerical features are the remaining ones. So I'll subtract from the original set. So if I look at the numerical features are age and kilometer driven. And now if I look at the categorical, the need for data transformation, so the categorical features have to go through the process of one-hot encoding, and the numerical features will go through the min-max scaling. We don't need to transform the categorical features or scale them because they are already on the scale of 0 to 1, right? So the value is either 0 or 1. So we don't need to scale them. So they will not be scaled, not required. They will be just one-hot encoded, and all the numerical features has to be encoded. So they will also come in the scale of 0 to 1. So now first I will set my X and Y variable. My X is now X features and Y is the price. This we have already gone through multiple times. And now I'm going to split the data into train and test. So X and Y, the train size is about 80% of the data and test size is the remaining 20%. So you can see about 808 samples in the train and 202 samples in the test data. Now the most important part, we're going to create a pipeline for KNN. Remember we did a pipeline creation for linear regression. I'll create a pipeline for the KNN. So we'll import all the required functions here. So in this case, we'll create those 2 pipelines, one for encoding categorical features using one-hot encoding, and one for converting all the numerical features using min-max scaling. So here one-hot encoder, I'll import one-hot encoder, and I'll create a pipeline saying that this contains one-hot encoding step, right? And this transformer, which contains this particular step of one-hot encoding, which can be applied to the cat vars, all the categorical features. Okay. Sometimes the pipeline can contain multiple steps also. Like last time I explained, sometimes you might have to, let's say, impute the variables first and then do a encoding, right? Or you do any other pre-processing step. Of course, for the timing, we don't have any values missing, so we'll just simply do one-hot encoding. And for numerical features, we will instantiate min-max scaling, and we'll create a num transformer which will apply the min-max scaling. And this would be applied to our num vars, numerical features. So here we define 2 smaller pipelines, each one for the respective type of features. And then finally we'll create the final preprocessor called column transformer. And here I am saying that the numerical transformer, which is the min-max scaling, should be applied to all the numerical features. And the categorical transformer, which is the one-hot encoding, will be applied to all the categorical features. So this is the pre-processing pipeline, which should be done before we build the model. And now here we'll import the k neighbors regressor. So all the regression, all the neighbors algorithm are part of this particular module called neighbors package, right? So KNN can be actually used for both the kind of problems. It can be used for regression. It can also be used for classification. So for classification, we have a class called KNeighbors classifier. So you have to import the appropriate class based on whether you are doing a regression modeling or a classification modeling. So in this particular example, we are doing regression. So we have imported KNeighbors regressor here. And we will instantiate that now with the KNeighbors regressor. Now the model takes two parameters. Unlike linear regression, which is just instantiated without passing parameters, now we have to pass these parameters. So we need this additional information besides the data that we provide to learn. We need this additional information. So in this case, the n neighbor stands for the k, how many neighbors we want to estimate, and weights is how the prediction would be made, whether in the simple average or the weighted average, right? So uniform means simple and distance means weighted average. This is, of course, we have hard coded here, but we can also, or we'll learn a technique called grid search later to find out the most optimal value for this, because they can be changed, or setting to a different value can alter the behavior of the model. Okay, so we have to tune them to the appropriate values so we get the optimal model. So these parameters are called hyperparameters of the model. So in this case, KNN has two hyperparameters. One is the k value, how many neighbors, and how the final prediction would be made, whether simple average or weighted average. And tuning them to the most optimal value to get the best model is called hyperparameter tuning. And this is, of course, a topic for one of the future sessions we will go through in detail. But as of now, let's hard code that. And if you look at the documentation of also KNeighbors regressor, and if you look at the n neighbors, number of neighbors to use by default, and weights is the weight function used in prediction. So if you say uniform, it says that all points in each neighborhood are weighted equally. So that means your yi that you're predicting is simply the summation of yi, I equal to 1 to k, 1 by k, because all are weighted equally. But distance is weights points by the inverse of the distance, 1 by d. That's what we calculate the weights. In this case, the closer neighbors of a query point that we want to predict will have a greater influence than the neighbors which are further away, right? So if you look at the calculation based on the weighted average, it would be the yi divided by the di, the distance, right? And will be normalized by 1 by di. Okay, so that will be the, so here I equal to 1 by k and I equal to 1 by k. So that will be the predicted value of the yi if you use weights as a distance, which is called the weighted average. Weighted average calculation. Okay. So now we'll find the build the final pipeline. It's called KNN pipeline now. Now this will contain two steps. One, the preprocessor. So whenever you give the data will automatically convert or transform based on this to different pipelines for numerical and categorical features. So we'll apply this preprocessor and then we build the model. And if you look at now the pipeline, it looks like all the numerical features, which are age and kilometer driven, has to go through min max scaling, and the categorical features, right? So your numerical features, age and kilometer driven, will go through min max scaling. Your categorical features, fuel type, transmission, owner type, and model will go through what? One hot encoding. And the outcome of this, both the pipelines after getting processed will come, and on that the K neighbors regression model would be applied. Right? Very standard streamlined way of building models. And all we have to do is now KNN pipeline will fit X train and Y train, and the model is built. Right? It would have done the pre-processing of both categorical and numerical features and fitted a model. Now a little bit of we'll look at in detail later what exactly does it mean fit here, because it's not estimating an equation, it's just finding neighbors. And how do we now predict on the test set how the model is doing here? So we'll predict on the test set. We'll say KNN pipeline predict the pipeline X test. Now X test will also go through the same process of pre-processing and prediction applying model, but in this case it will not call fit, but will automatically find the neighbors for each of the test case. For example, the first test case X test 0, right, is going to find neighbors. Which are the neighbors which are available in the extreme? And how many neighbors? 5 neighbors, because that's what we have set in the model. So each of the test case in X test is going to find 5 neighbors in the train data, and from those 5 neighbors price value is going to estimate the price of this based on the weighted average, based on what we have used here. We have used uniform simple average calculation, right? We have done simple average calculation. So based on that, so let's now predict, and the prediction values are captured in y underscore pred. So you can go and find what's the R square value. So the R square value comes out to 0.86. Okay, very similar to the one that we have got in the linear regression model. I think linear regression model also got about 0.86 and 0.87. When you use only the 6 features, of course, when you use all the features, the value might of course go beyond 0.9. That I leave it to you for as an exercise. So can we predict on the new data now? So let's say there's a new car, and these are the values of the new car, new used car. It's a diesel car, it's a manual, first owner. It's about 8-year-old, an Artiga, and driven for 87,000 kilometers. So that's given in dictionary. We have to convert that into a data frame and simply call the KNN pipeline on that. And basically says the car would be sold at a 6.07 lakhs. So that's how we can build a KNN model, and we have to take care of the pre-processing step. Very, very important that we apply this, right? The scaling technique to the numerical features, and of course one-hot encoding is required for categorical features, and then we build a KNN model. And in this case, of course, we hard-coded the number of neighbors and the weights. So one thing that you can experiment with it after the session is over, you change this particular value, right? We change this particular value to distance, which will calculate the weighted average and see what influence it has on the accuracy. Okay, so experiment with the different values of a number of neighbors like 5, 10, 15, and also change the value of the weights, uniform sometimes and weights distance sometimes, and see what influence it has got on the accuracy on the test set, the R square value. As a first exercise, you can find out how many neighbors is optimal. So find out how many number of neighbors gives the best accuracy on test set. So what you can do is you can create a loop, for loop. and loop through many possible number of neighbors like 5, 10, 20, or you can say 5, 6, 7, 8, 9, or 5, 7, 9, or something like that. From starting with 5, let's say, ends with 30 or 40. Build models with a different number of neighbors. You take that particular value and build a model, measure R square, and print the number of neighbors and accuracy score. For example, let's say for 5, what's accuracy? 0.86. For 10, what's accuracy? For 15, what's accuracy? Right? And then you see which number of neighbors gives you the best accuracy. So this you can do for number of neighbors, and you can also alternate like how many number of neighbors, 5, and uniform, like a simple average calculation. So what is the accuracy? 5 for distance, weighted average calculation, what's accuracy? Then 10 uniform, and so on and so forth. Then you can see which combination of these two parameters gives you the best accuracy. So that will be a wonderful exercise for you to do. And there is of course a better mechanism to do this using something called a grid search, which we'll explore in one of the future sessions. But let's do that as an exercise for you. And the second exercise is build a model with all the variables from the data set. So we haven't used, as of now, in this modeling exercise, we haven't used location, number of seats, mileage, and power. So add these 4 more variables and see how the accuracy changes. And for that also you can find out how many neighbors would be optimal. So build the model with all the variables from the data set and use the above approach, this one, to find the most optimal value of a number of neighbors, and probably also weights, whether it's a uniform or distance, which gives the best accuracy on the test. So this will be a good exercise for you to get little more hold and grip on this particular algorithm and how it can be used. And with that, I think we'll end this session today, and looking forward to the more advanced session in the future sessions. Thank you.